So we already talked about the linear probability model, where we code a binary dependent variable as a 0 or 1 and then estimate the linear regression. And we call it the linear probability model because we can probably best interpret the predictions we then get as probabilities, because we get values very different from 0 or 1. We get values a lot of values between 0 and 1 and occasionally outside 0 or 1. And so probably the easiest way to interpret that then is to say that we are estimated probabilities. And then we can come up with some decision criteria. For example, say that whenever the estimated probability is greater than 0.5, we assume that it is a 1, and otherwise it's a 0. But this approach has a number of disadvantages, even though it is quite common in economics, and when the task is prediction, it can work fairly well. The disadvantages are that in some cases you will get estimates outside of 0 or 1. So you will get the predicted probability that is greater than 1 or less than 0. And this is just logically not sensible. Now, when you are just doing a prediction based on this 50% threshold, then maybe it's not a big deal. But strictly speaking, it's not ideal. The second thing, which is probably more important, is that you get unrealistic effects, in the sense that when given other x variables, the predicted probability of a 1 is already very high, or the predicted probability of a 0 is already very high, then any additional effect cannot have much of an impact. So maybe x1 and x2 already lead to a very high probability of a 1, and then x3 also increases. But if the probability is already very high, it can't go up all that much. So we should have a curve that flattens off at the top and bottom ends, where the effect of a change in x is much higher when the probability is close to 0.5 than when the probability is close to 0 or 1. The third problem has to do with the t-tests, and so we are not interested in that too much here. We are not really looking at the statistical tests, but when you do the statistical tests, the linear probability model does lead to heteroscedasticity, which renders the test somewhat unreliable. That's really a little bit outside of this course. So we would want to get to an alternative where we maybe look at the linear relationship in first instance, but we want to address these shortcomings. So one way to address this problem is to first take a linear prediction. So a linear prediction means you come up with, estimate some coefficient, and you multiply every variable with its associated coefficient, and then you get an overall average value. That is exactly what we do in linear regression. But instead of taking the linear prediction, we transform it first. And the graph that you see here shows how this transformation can work. So in this transformation, the linear prediction is on the x-axis, and on the y-axis we have the transformed value, which is now first of all between 0 and 1. It never goes outside. It can take on any value between 0 and 1. And you can see that the steepest slope, so the strongest effect, is indeed in the center, where the predicted probability is 0.5, the slope is steepest. Whereas at the end points, where it is 0 or where it is 1, you see that it tapers off. And any effect in x, any change in the linear prediction, has a much smaller effect on the predicted probability when the predicted probability is already very low or already very high. And so this addresses all the concerns that we outlined in the previous slide. So this slide shows how that transformation looks mathematically, but you don't have to worry about this too much. We are basically taking a linear prediction to be not the predicted probability, but the log odds ratio. If you are a gambler, you might be familiar with odds ratios. So it is the probability of observing a 1 relative to the probability of observing a 0, and then we take the log of this transformation, this ratio, and then we get something that can reasonably predict with a linear model. And that transformation is exactly what you saw on the previous slide. That is the curve that you saw. And we call this logistic regression. It's relatively straightforward to implement in R. It looks very similar to a linear regression, but you have to make explicit that you're looking at the logistic regression. The regression table that you then obtain also looks similar to that for a linear regression. So you get for each of the independent variables a coefficient, and perhaps in percentages below it the standard error. We are not going to discuss standard errors. because that is more for a statistics course. What is similar with linear regression is that the positive signs refer to positive effects. If x increases, y increases. Negative signs refer to negative effects. And 0 refers to a relation where there is no relationship. And if you want, you can look at the stars. They show the significant, statistically significant relationships. The relationships where we have enough evidence that this is really happening. But again, this is the inferential part we don't look at. Just look at the positive and negative signs. Now the only difference is that with the linear regression, the size of the coefficient is relatively easy to interpret. Something like, if the coefficient is minus 2.5, you can say if x increases by 1, the y goes down by 2.5. That is not so straightforward in logistic regression because of this nonlinear transformation. And just as with discriminant analysis or with the linear probability model, we can go to our fake data set, we can estimate the logistic regression, and we can figure out the decision boundary, the line in a plot of x variables that separates the groups on the y variable. So here you see that line. In this particular data set, the decision boundary between the logistic regression, the linear discriminant analysis, and the linear probability model, they differ very little. So the results are actually quite similar. But in other data sets, the variation might be larger. Yeah, so this is artificially generated data, so it has particularly stylistic shapes, and then these models don't differ much. But with real data, you will see larger differences. So there are a number of advantages and disadvantages when one chooses between linear discriminant analysis and logistic regression. So in especially in machine learning data science applications, you want a careful consideration which one works better. In the social sciences, we actually in published articles where we are doing more causal inference, LDA is just quite uncommon. Now, one thing that is where they differ is in terms of outliers, extreme observations that are very different from all the other observations, that differ a lot on the x variables. LDA is quite sensitive to this because it's focusing on means, and the mean is always strongly affected by outliers. This also affects the LDA estimator. Logistic regression, it's quite robust for outlier data. So when you have outliers, so data points that are really far from all the other points, logistic regression might be more robust, might be better able to handle this. The second point is that LDA assumes that x is normally distributed. It has this bell curve shape. So on all the x variables, you would expect most values to be somewhere around the center, and then to be a bell-shaped curve around this. This is of course not always the case. Logistic regression makes no assumption about the distribution of the x variables. Now, if the assumptions of LDA hold, so you don't have major outliers, it follows a more or less normal distribution, then LDA is more efficient and it comes up with slightly better predictions. It's more precise than logistic regression. But logistic regression would be a bit more robust and would be able to handle different types of x and outliers. One technicality, if you could draw a line through those points that perfectly separates the two groups, then almost by definition there are many such lines you could potentially draw. And logistic regression, for that reason, gets into trouble. So if two groups are perfectly separable, if you could draw a line that exactly separates all the gray from all the black dots, then for LDA this is no problem, but you will not be able to estimate the logistic regression. And the way you can think about it is that there will be many lines that would separate the two groups. It would be difficult to come up with the line, and so logistic regression fails. And finally, when the data is very imbalanced, so when you think about the ones and the zeros, if there are many more ones than zeros or many more zeros than ones, then logistic regression is more robust to this as well. So logistic regression, more robust, but LDA is able to deal with perfectly separable data and can be more efficient when all the assumptions are met. We discussed with linear regression that there are regularized versions, so you can do stepwise regression or lasso or penalized regression. Regressions where the beta values, the parameter values are pressed down, are kept low, so that more important variables weigh more heavily, and so we get simpler models. And these models tend to be a bit more robust when we want to go to new data sets. For logistic regression, perfectly similar methods exist. They are a bit beyond this course, we can't cover everything. But just so you know that the types of regularized regression that exist for linear regression, they are equally available for logistic regression.